Well, hi there. We're going to have a look at polynomials today in what I call as, quote, turning point, unquote, form. By that I just mean that they're not exactly in turning point form like we have for quadratics, but they're in the same general form of the equation. So there's a linear factor, x minus something in brackets raised to a power n plus some constant. That's what I'm talking about, so please don't send me to the mathematical tribunal. It's not actually turning point form, it's just the same kind of equation form for different degrees of polynomials. Alright, now polynomial form, yes, that's it. That's what I was trying to say. Y is a times x minus h to the n plus k, where n is a natural number. And these have the same form as quadratics in turning point form, right? The same form of the equation, but some of them aren't turning. So please don't think that I mean that they're turning, because if they're even, they do. If the exponent is odd, that is, they don't. So let's look at the two cases when they're odd and when they're even, right? And we'll look at trends as n increases, and we'll also look at some transformations for each. So, have you got a nice cup of tea? I've got a nice cup of tea here, and we'll just fasten our seatbelts, and you pause the video and get a cup of tea if you like, and off we'll go, okay? Right, now, when n is odd, okay? Yes, n would be 1, 3, 5, 7 if it's a natural number. Alright, I don't mean negatives, I just mean natural numbers, 1, 3, 5, 7. The trend is your friend. Let's have a look at this. That's y equals x, yes, you're very familiar with that. Now let's do x cubed, x to the 5th, x to the 7th. You get the message. Actually, we dealt with a lot of this kind of stuff back in 3A, families of functions, didn't we? Where we did a bit of an expose similar to this, didn't we? Okay, if not, if you didn't see that, go back and have a look. It's worth having a look at, I think. It'll help you a lot understand the trends. And the trend is your friend. So, right, now, as n goes up, the curve bends towards the x-axis more and more when you've got x between 0 and 1, like that, and like that. That's when x is between minus 1 and 0, in that latter case there. But then when x is 1, okay, they all pass through either 1, 1 or minus 1, minus 1. You get that? That's here and here. And then, of course, when n is greater than 1, the curve bends away from the x-axis more, like that. Or when it's less than minus 1, it also does the same thing, bends away like that. Yeah? Pretty clear, isn't it? Okay, they're the trends, and the trend is your friend. Yes, it is. Now, here's some transformations for you. Let's do a cubic one, okay? This is a cubic. X plus 1 all cubed minus 1. So, we have to sketch the graph of it. So, let's work out the transformations first, and then we can basically apply those transformations to the perfect cube of y equals x cubed as the base model function. All right? Okay with you? Great. Now, okay, so we're going with this notation here, the dashes, or the primes, as some people call them. Y dashed equals x dash plus 1 all cubed minus 1. That's a transformed function. And what I'm going to do is I'm going to work out the steps that were involved to get from here to here. Now, in all the videos on transformations, I called that a backwards transformation calculation because we're given the starting base model function, the final transformed function, and we're actually working backwards to find the steps, and those steps will then enable us to then correctly move the base model graph of y equals x cubed, in this case, to our new location for the transformed graph, okay? So we've got y equals x cubed is our base model, and I'm putting it in equivalent form, okay? Y dash plus 1, I've moved that thing over there because he's not belonging to anybody, he's not attached to anybody. And if you don't get what I'm talking about there, go back and look at the transformation videos, the 3 series of videos, okay? That'd be 3B, C, D, E, F, G, I think, about that area. All right, so yes, so there we go. So that's that. They're in equivalent form, so we can actually equate like terms now. We can say y dash plus 1 is equal to y, and we can say that x dash plus 1 is equal to x. Now, because we're doing a backwards calculation as the videos in the 3 series videos would have indicated, we make y dash and x dash the subject, right? That's y dash, that's x dash, and now we can just rattle off the transformations, because basically to get from y to y dashed we have to subtract 1, which means we're actually going down 1 in the y direction. To get from x to x dashed, we have a translation of 1 unit. That's wrong. Wait, am I fix that up? Sorry. Okay, sorry about that. I must have got a bit dyslexic. I had the word down there. It's for the x, it's a translation of 1 unit to the left. Okay, now we're right again. Pardon the pun, but we're right again by putting left there. Now, that's pretty easy, isn't it? Now we can actually work out what our transformed graph is going to look like compared to the base model graph of y equals x cubed and the RGB. Now, what we've got here is this red one is y equals x cubed, but we've taken this stationary point of inflection here as a reference point, and we've moved it to the left by 1 and down by 1 to get this black graph equivalent stationary point of inflection position. We don't need to work out any more because this thing actually goes through, this black graph actually goes through the origin, so there aren't any other intercepts for us to work out. Everything's good, isn't it? See, do you get the idea? We're just using transformations as the steps involved to get from x cubed to this, and to work out the steps involved in getting to this. Once we work out those steps, we can then apply them to the base model graph to get our new graph, okay? Just gets us a sense of proportion and a sense of reasonableness of what we're doing. Now, what's this one? Find the rule for the image of the graph of y equals x to the 5 with the sequence of transformations. Okay, I get this. This is what I call a forwards transformation calculation. We have to come up with the rule. We don't have to do the graph, we just have to get the rule. Reflection in the x-axis, dilation of a factor of half from the y-axis, and a translation of plus 3 units in the x direction and plus 2 units in the y direction. That's all right. It's the same old, same old. This is just basically a transformations question, guys. But we're doing it on these particular functions, right? Yes? All right. Right, I'm doing a pictorial representation for you now. So if we have a reflection in the x-axis, there's our random point, x and y. I usually draw a quadrant 1 point. So let's go there, to there, to there, to there, to there. Yeah? That's a reflection in the x-axis, isn't it? Good. Now that's, what have we got to do now? A dilation of a factor of half from the y. Now you visualise in your mind where that's going to go from this position here to do that. Right? From the y, factor of a half. Well, that's 0.1, yes. But now we're going to do 0.2. There it is. You see, we went basically in there so that we basically, dilation from the y basically as a reference point, which means the x gets changed, right? The x gets changed. We go down to a half x from the original point here of x, yes? The y doesn't change. The y doesn't change. That's 0.2. Okay, got it? Here comes 0.3 now, a translation of 3 units in the x direction, positive, and 2 units in the y direction, positive. So just have a look at it. Have a look. That's there. We're going to go 1, 2, 3 that way. These little red dots are trying to indicate what we're doing. Then we're going to go 2 units up. 1, 2. I just tried to do that to show you. And that's where we're going to end up, guys. There. Okay? So we've added 3 to that point and we've added 2 to that point, as you can see. So I think everything's good. So that was what we did from the first one. We reflected in the x-axis, didn't we? Yes, so the y got changed to minus y. Number 2 was, okay, what was that? Dilation factor of half from the y, therefore the x changed to half its value. Yes, and the third one was, what was that? Adding 3 to the x and 2 to the y, that's right. So that's our transformed point. That is our transformed point, x dashed, y dashed. Now, what I do now is I do what I call the key to everything, because that x dash and y dash is equal to this. Now let's just state that as my amazing key to everything. So x dash is the same as half x plus 3 and y dash is the same as minus y plus 2. Now with the forwards calculation for transformations, if you remember from the video series that I did on that, you make x and y are the subject, right? X and y are the subject, and you plug them back into the original rule, that in this case y equals x to the 5, right? So x would be that, making x the subject, y would be that, making y the subject. Now we're going to plug them into the original star equation, as I call it in the transformation series, and we will get that, yes, in terms of x dash and y dash, for x and y in terms of x dash and y dash, this stuff down here. That's the key to everything, those two equations, right? It is the key to everything in transformations. Makes them easy as easy can be. Now we've just got to sort of fiddle with that a bit to make it look a bit more friendly, and then drop the dashes. So that does that make sense to you? Wait a minute. Y dashed. Yes, that's right. That's right. Now drop the dashes for the final answer, because our caterpillar function is transformed into its new butterfly version, doesn't need to remember where it came from. That's it in its own right now. There it is. That's our rule for our transformed function in accordance with this recipe up here of transformations. Okay, are you good? If not, you might need to go back and look at the transformation video series. They make it really, should make it really clear for you. Now, what's this? This one is state a sequence of transformations, which would take the graph of y equals x to the 5 to the graph of that. Well, this is what I call a backwards calculation, because they give you the start, they give you the finish, and then you have to work backwards to the steps. Now, you watch the slight difference with which I treat the key to everything in this calculation compared to the previous one. So y equals x to the 5, that's the equation of the original function. Y dashed equals this thing here. I'll put dashes in for y and x to denote that this is the transformed function. Now, what we've got to do now is get them in equivalent form. There's the first one, the original. There's the second one in what I call equivalent form, which means I can now basically equate the y terms and the x terms, right, as equivalent. So doing that, that's an equivalent statement of the y's, that's an equivalent statement of the x's, and I'm going to make, in this case, I'm going to make y dashed and x dashed the subject, and then just read off the transformations which we've done to x and y to make them x dashed and y dashed respectively in a logical way. So that's what y dashed is, that's what x dashed is. So I don't make x and y the subject as I did in the previous forwards calculation. I make x dashed and y dashed the subject in a backwards calculation. Hope I'm making sense. You will have needed to watch the video series on transformations to really get this. Now, I can just read them off. I can just read them off, rattle them off as the steps involved. So that's that now. So from equations 3 and 4, to go from x and y to x dashed and y dashed respectively, we need, right, this is the x done first. So what we need is a dilation. Yeah, this is the, no, I'm doing the y first, I'm sorry. This is a dilation of a factor of 3. That y has got to be 3 times as big as it was before, so that's from the x-axis. This little beastie here is a reflection. So y is reflected into the negative y. That means it's a reflection about the x-axis. So there's those two statements dealt with there. That's the minus and the 3. And then the 5, that means that its y is going 5 units up. All right? Have a look. You get it? Okay. Now this x is just going to be translated 6 units to the left to get to x dashed. Yeah? See, easy as. And we've got our answer. We've done it. Thank you, Mr. Box. And there we go. How do you feel? You feel okay? Well, I think that's the odds. We better do the evens now. Okay, remember we were doing odds and evens, and for within each of those we were going to do some transformations and translations and things. Now these are a different class of functions, these even ones, right? When n is odd, they come in one end of the y-axis and go out the other. When n is even, they come in and go out the same end of the y-axis, as you will see. Here's the trend, and the trend is your friend, see? These come in this away, and they go out that away, okay, if you like, as you go across the page from left to right, if you know what I mean, in terms of x. They come in up here, they go out in terms of that direction, they go out the same way. The odd ones are different, yeah, as I just explained. That's x squared, x to the 4th, x to the 6th, and x to the 8th. My goodness. Can you see the trend? Because the trend is your friend. Yes? All Alright, so what are we saying? As n increases, the curve bends towards the x-axis more and more when x is from 0 to 1 and there, and x is between 0 and negative 1, don't they? Don't they? Yeah, when x is 1 or negative 1, they all pass through the same points. Yes? 1, 1, minus 1, 1. Yeah? And as n increases, the curve bends away from the x-axis more and more for x is greater than 1 and for x is less than negative 1, as I'll show you with arrows. Stand by that one and that one. Okay? Yeah? You get it, don't you? That's the trend. Now here comes the transformations. Alright, so this one here, the graph of y equals a into x plus h to the fourth plus k. Okay, that's kind of like what I was saying is like the turning point form, if you like, which is probably more appropriate for the even functions because they really do turn. They turn just like the quadratics, yeah? So, okay, as a turning point of 3 and 3, and it passes through the point 0 and, my goodness, is that 84? 84? Good heavens above, what a large number. Well, we are dealing with a quartic, ladies and gentlemen, so it's probably logical. Find the values of A, B and K, H, and K. Alright, today, hooray, here we go. Turning point is 3 and 3, so you plug that straight in. You just plug it straight in. So H is 3 and K, no it isn't, H is minus 3, I beg your pardon, and K is plus 3. Yes, just in the same way as you do for the quadratics, yeah? Okay, so therefore in that case y is going to be that with the H and the K substituted in. Now all we've got to do is find the A, and we do that by substituting this other point into the equation, 0 and 84. So here we go. There it goes. And if we just plug away at that, we can probably... x is 0 though. X is 0. So therefore, 3 to the fourth is 81. So you get 84 equals 81a plus 3. Therefore it looks like... Yes, looks like A is 1. And we're done. Look, isn't that great? So we've got our answer. Now what did the question ask? Find the values of A, H and K. We've done it. We've done everything asked for. Full marks for us. Yes? Oh, that's the end. And the trend is your friend. Okay? So, hope you enjoyed that. You know what I mean by turning point form, in quotes. Yes, it's probably more appropriate for where n is even natural numbers than it is for odd, but the form of the equations are the same as you have for quadratic turning point form. Okay, there you go. Hope you enjoyed it, and we'll see you next time. Bye for now.